So we're back at this problem, trying to think about whether the series converges or diverges, and we looked at S sub 1, S sub 2, S sub 3, S sub 4, and it's clear that, I mean, just looking at these numbers, that it looks like S sub in S sub n is a probably, as n gets close to infinity, it's probably getting close to 1. I mean, these values are all getting close to 1. But let's see if we can prove that even more. So if we look at these values, we've got 1 over 2, 3 over 4, 7 over 8, 15 over 16. What we need to think is there some way that we could express as S sub n in an equation? Well, first thing, notice that the numerator is always 1 less than the denominator. So the numerator is always 1 less than the denominator. And we've got 16, 4. 2 to the 4th is 16. 8 and 3. 2 to the 3 is 8. 4 and 2. 2 to the 2 is 4. Hopefully you're getting to where I am right now, which is that we could express S sub n as 2 to the n over 2 to the n minus 1. And, um, without getting into L'Hopital's rule, we can see that as n gets hugely big, this minus 1 doesn't really affect it at all, and we have 2 to the n over 2 to the n, which is roughly 1. So that's the next step, which is taking a series, writing out the series for the first couple values of n, identifying a pattern, and then trying to take S sub n and write an expression for it to see whether or not the function converges or diverges. So let's do that again for a different sequence. We've f of n equals 1 over n times n plus 1. And it says find an expression for S of n, S sub n. And then use that expression to see whether it diverges or converges. So let's generate a couple values. S sub 1, 1 over 1 times 1 plus 1, 1 over 2. S sub 2, 1 over 2 times 2 plus 1. Sorry, this is, well, S sub 1 equals A sub 1. I'm not finding S sub 2 yet. This is just A sub 2. And this equals 1 over 6. So S sub 2 is the sum of these two terms, A sub 1 plus A sub 2. So 3/6, which is 1/2, plus 1/6, which is 4/6, or 2/3. And then we need to find S sub 3. So we want to be identifying a pattern. So S sub 3, well, that's S sub 2 plus A sub 3. So we have 2/3 plus A sub 3. Well, that's 1 over 3 times 3 plus 1, which is 1/12. So we get 2/3 is 8/12. So getting a common denominator, plus 1/12 equals 9/12, or 3/4. So we go S sub 1 is 1/2, 2/3, 3/4. Let's do one more of these, and this is very similar to the last one. If we do one more, we have S sub 4, which is S sub 3 plus A sub 4. So 3/4 plus A sub 4, which is 1 over 4 times 5, 1/20th. So we get 15/20, re-expressing this one, plus 1 over 20 is 16 over 20, which is 4/5. So now we need to think about, well, what's the pattern that's going on? So take a second to see if you can write S sub n in an equation. If you can't, well, pause it, see if you can. If you can't, unpause it, and we'll do it. Okay, so S sub 1 was 1 over 2. We had a 1 and a 2. S sub 2 was 2 over 3. S sub 3 is 3 over 4. S sub 4 is 4 over 5. So a good correct answer would be S sub n is n over n plus 1. And we know that, to see whether this diverges or converges, the limit as n approaches infinity of S sub n, or n over n plus 1, as n gets hugely close to infinity, using L'Hopital's rule, this is the same as the limit as n approaches infinity of 1 over 1, which equals 1. Therefore, since it approaches a number, the series converges, and it converges to 1. So here's a test to see if something converges. And it's really not a test to see if something converges. It's really a test to see if it diverges, because it's inconclusive for convergence. So we know, I was writing this the other way. I was writing this way in the last couple examples, but S sub n is the sum of all the terms before it, S sub n minus 1, plus the new term, A sub n. The way I was writing it before, just so that we're familiar with this, I was saying like S sub 4 would be equal to S sub 3, the sum of the first three terms, plus A sub 4, plus the fourth term in the sequence. And the idea is, if we think about convergence or divergence, in order for S of n to converge, it needs to eventually reach some fixed amount. And for it to reach some fixed amount, what must be true about A sub n when n gets huge? In other words, what must be the limit as n approaches infinity of A sub n if for S of n to converge? So if S of n converges, what must be true about the limit as n approaches infinity of A sub n? Well, for S sub n to converge, we can't keep adding things to it. It must reach some fixed amount. So my nth term must add negligible amount to my series. Negligible amount meaning that as n approaches infinity, A sub n must approach 0. So that essentially I'm adding 0 to my series. And if I add 0 to my series, then I'm not adding anything. And if I'm not adding anything, then it converges. So conversely, if the limit as n approaches infinity of my last term, A sub n, if it doesn't equal 0, then what must be true? Well, then S sub n diverges. It doesn't approach some fixed amount. So this is just what I wrote. If the series converges, then the limit of the last term must be 0, that we're adding nothing to it. And then the converse being, if it doesn't equal 0, if the nth term doesn't equal 0, then the series must diverge. Because if it doesn't equal 0, then I'm adding things to my function, and it's getting bigger and bigger and bigger. The important thing, though, is that this top statement is a one-way highway. In other words, if the series converges, I know that the limit must be 0. But if the limit equals 0, that doesn't necessarily mean, it does not mean that the series converges. So this is true. If the series converges, the limit is 0. But if the limit is 0, it doesn't necessarily mean the series converges. And we'll look at that in the next couple of examples. So does the series below converge? We want to know, does this reach some fixed amount? And this is a tricky limit problem that they threw on here. They give us a hint. They say let 1 over n equal t. So we know that we're going to need to use that. So if 1 over n equals t, similarly 1 over t equals n. So we could replace the following with the sigma notation. Instead of n, I have 1 over t. And then we have sine of 1 over n. Well, 1 over n is t. And then we need to replace our limits. Well, when n equals 1, t equals 1 over 1, which is 1. And when n equals infinity, t would be 1 over infinity, which is 0. So this is going from t equals 1 to t equals 0. Now, if I want to use the theorems that I was looking at before, the test for divergence, I want to see if the limit as n approaches infinity of a sub n equals 0 or if it doesn't equal 0. So, I've rewritten it right here, but let's do this to keep it in terms of n. What I'm saying is, if the limit as n approaches infinity of n times sine of 1 over n, we want to know what that is. If it equals 0, then it may converge. If it doesn't equal 0, then it certainly diverges. So what we do, well, let's replace this n's with t's, and we can get the limit. Well, as n approaches infinity, t is approaching 0. So the limit as t approaches 0 of sine of t over t. And this is a very famous limit problem that you've looked at calculus AB for sure. But if you need a reminder, if you take this function and you graph it, you get something that looks like this. It's a beautiful graph. It's got a hole there, and then it comes down, and that value is 1. And so you could use a squeeze theorem or other theorems to prove what this limit is. We could use L'Hopital's rule, actually. Let's do that. Let's use L'Hopital's rule to see what this is. So the limit as t approaches 0 of sine of t over t is the limit as t approaches 0 of cos t over 1, which is just 1. So therefore, we just showed that this limit equals 1. So going kind of up the street, this limit then, since they're the same, equals 1. And since the limit equals a number not 0, since this isn't 0, we can say that the series S sub n diverges, since the limit as n approaches infinity doesn't equal 0. And again, the idea being that the nth term is adding a substantial value. It's adding 1. The nth term continues to add 1. As n gets close to infinity, we're just adding 1 and 1 and 1 again. Because this value here, that is our nth term. So we continue to add value to our sum, and if we continue to add value to our sum, it's going to diverge. So I'm gonna pause the video here, and we've got more in front of us.